Can you guys hear me okay on the speakers? Yeah, okay. So, I've just got a quick lecture, less than 20 minutes. It's basically going to cover some useful strategies for what to do when things don't go well. And this can happen from time to time. And so we'll get started here. So with OpenACC, we're giving a lot of control to both the compiler and the runtime. And the user is giving up a lot of this control. And so there are a number of issues that can happen. And the key is to understand basically where it's happening by gathering in as much information as possible from the compiler and the runtime. In terms of a lot of different issues that can happen specific to OpenACC, we can have basically a code that doesn't run on the accelerator and maybe we don't even realize it. We can have 10 times slower execution than on the host. We can have wrong answers, inconsistent host device data where there's a mismatch between the updates. We can have a bunch of different types of CUDA API errors. So many different issues above and beyond what you're dealing with on x86 and with CUDA. And it can be challenging because we don't have printf within the accelerator regions. So the big question is, how do we troubleshoot things? And there are a number of different strategies that are helpful. So today's lecture is just going to go over a bunch of different strategies that are useful. Maybe a lot of these aren't going to be useful for your own codes, but maybe some will be. And we'll go through each one of these. I'll just go through the list really quickly. With the first thing you might want to try out is making sure that your code runs is parallelizing correctly with OpenMP. And I'll show an example of this later. Another thing you might want to look at is looking through all your compiler messages, looking for various warnings, because remember, it's a conversation between you, the compiler, and the runtime. So these things are even more important than when you're running on the host. How to investigate the runtime output. This is critical. Comparing between different compilers and runtimes, and basically, like I mentioned before, gathering as much information as possible and making decisions based on all the information that's being provided to you. Various Nvidia tools can be helpful, and trying a more traditional debugger, and I'll show an example of this at the very end. So a very good strategy is actually to start with an OpenMP code and use that to port to OpenACC. And there are a number of reasons why this might be interesting, because obviously the debugging tools are much more rich and plentiful on the host. So you can tell if you're having parallelization issues with the various kernels, much easier if you're running on the host. Let's see, you don't have to worry about the host device data transfers if you can leave that to a later stage. And yeah, so this can basically reduce the amount of trouble you see with your OpenACC code if you have confidence that an OpenMP version is running correctly. Another strategy is basically looking through all of your compiler messages and making sure that you're not getting strange warnings and things like this, and understanding what the difference is between positive message from the compiler versus a negative message. And this is an example of something that you might see that is more of a positive message. And here we can see a very simple code or a loop structure, triply nested loops. We've got the accelerator directives here in green. And the messages, these are from Cray, obviously, using -h list equals m. And the compiler is basically telling us that the code was placed on the accelerator. It's using pre-allocated device data, or it's going to issue a copy if it's not already over there. It's doing collapses at this level here. And the compiler is basically able to successfully partition the loops. And some of the things you should always be watching out for, they're not necessarily errors, but you should understand what these mean and try to understand if that's what you think should be occurring in your code. So some simple examples, if your code isn't vectorizing, you always want to deal with that. These two examples down here can be, you might find it in a code that's running quite well, maybe in the innermost or the middle loop. But these are just examples of things you should, kind of like red flags, you should consider in your own codes. In terms of PGI, we can see the different format here. And all the different compiler messages from the different implementations are giving similar information, but in different formats. Again, you can see in the messages here, we're using present clauses. So it's telling us similar information. And it's basically successfully partitioning the loops. We can see the kernel was generated. That's a good sign. In terms of some of the more negative messages you can run into, things like dependencies, things requiring privatization, situations where specific to the accelerator, let's see, unsupported operations, certain features not supported. So pay attention to your compiler messages because they're critical when you're dealing with directives. In terms of caps, you can add this flag here that actually dumps out a bunch of information. And you get, again, a different type of message from caps, but it's telling you very similar things to the previous two examples. And so in this case, I wanted to show a simple scenario where we've got a triply nested loop, and we're using a parallel directive here. And we compile and we run, and we find that, wow, we know it's running maybe 10 times slower than on the host. And so we go back and look to see what the compiler was doing, and it just dumped out a message saying that it partitioned across the various gangs. But there's no information about the vectorization that happened. So that should be a red flag, and you want to pay attention to these sorts of compiler messages. So if you add more specific loop directives, the compiler is able to add these extra messages here saying that the loop I was vectorized, and that's what we want. And in this case, we actually get decent performance. You know, it's a huge difference. So pay attention to your compiler messages because it'll save a lot of trouble. Moving on to runtime output. With these various slides, I just wanted to show you certain things that you should be aware of, and so that you're more familiar and you're not afraid to dig through all the logs, because there's really a lot of useful information in these, in the runtime output. So all you have to do is set the environment variable with the Cray implementation. You set this environment variable, and when you run your code, the runtime's spitting out a bunch of information about what it's actually doing. And you can get information about the data transfers, how much data is being transferred, where the basic, the piece of an array was found. You can get information on a number of different things. You can get information about kernel launches. You can get information about the number of blocks that are being used, the threads per block, the number of registers being used. So this is all really essential information, both in terms of performance and functionality. And so each implementation of OpenACC has a different format. This is PGIs. You can set these various environment variables to get this output similar to Cray. Again, it's showing you that it found the array on the device, in the device memory. It's doing some initialization here. It's allocating some local storage. And it's launching the kernel. Right now, maybe you guys are thinking this is a bit too deep, but when you're running a full application and you run into problems, you're going to need this sort of information to figure out what's happening. Moving on to caps. So here's the environment variable for caps. It's telling you that you're entering data regions, entering parallel regions, allocating data on the device. It's telling you that it's the shared memory. It's talking about launching kernels on the device and giving the various kernel configuration information, freeing storage. So there's a lot of information you can get. Another really useful strategy when you run into problems is comparative debugging, where you run your code, you compile your code using one compiler, try to run it, and maybe in this example, it compiles fine, it runs, and you hit some strange CUDA error that you have no clue what it means. You switch to a different compiler, and you try to compile it with that different compiler, and it's warning about a specific line number. And all of a sudden, you have a lot more information just by switching over to a different OpenACC implementation. And then you fix that line number and rerun everything, or rebuild everything with both different compilers, run everything. And these sorts of situations seem to pop up quite often where in real application development, you're switching between one implementation and another based on the information that a certain compiler is giving you, or whether or not one specific very tiny feature is supported in a compiler. So I think it's very common to switch between implementations. You can use some of the Nvidia tools with OpenACC. CUDA Memcheck is one thing you can use. Maybe tomorrow we'll hear more about CUDA Memcheck during the CUDA specifics talks. But you can use it with OpenACC. You can get information about where, similar stuff that you can get from the Memcheck on the host, you can get on the device as well. Information about maybe where you got a seg fault in your device code, and it gives you information about the line number, the specific error. Maybe we'll hear some more tomorrow about it. Another useful Nvidia tool is using these timeline GUIs. Basically NVVP, which is the CUDA profiler. You can gather a bunch of information during a run, and it'll just basically display the timeline about where your kernels are launching and the orderings. And this all helps you to visualize your code over the length of of your program. It can also be useful for understanding the asynchronous behavior in your code. And on to another strategy is using DDT's debugger. And we actually have this on Toady, so you can try it out over today and tomorrow on these codes. So the status with DDT is that they support CUDA and OpenACC, but there are some ongoing issues that we're working through. But we still encourage you to give it a try. With the various compilers, DDT requires dwarf support. PGI is working on this. CAPS, I think, I tested it recently, and it seems to work okay. Cray, as far as I know, it works pretty well. I don't know what the limitations are, but there's dwarf support in the host and device code. In terms of capabilities, what can you do with DDT? If you're familiar with Total View, it's very similar. You can basically set breakpoints within the host or device code. That means if you have an accelerator region, you can set a breakpoint within the accelerator region and run to that specific point. You can step through the various kernels. You can inspect variables and arrays on both the host and device. It's fairly easy to use, but again, we're ironing out some of the issues. With the Cray compiler, all you have to do is load the module and basically add a -g. There are certain cases where adding this -g will change the, I guess, how the compiler does the loop scheduling. And you may run into problems with this, but you can try changing the optimization levels, and perhaps this will help out. And one of the workarounds we've caught on to is that if you have a scalar code that has no MPI in it, you may need to add a dummy MPI init call within your scalar code. And this is actually because of how the DDT runtime is happening is working along with the AP run scripts. So here's kind of a screenshot about the sort of information you can get from DDT with an OpenACC code. Up here you can see some of the controls for executing the DDT job. You can see a breakpoint here within an accelerator region. You can see the various kernels that are running or not running. Over here we have information about the local variables to each thread, and here we've specified thread 16, and so it's giving information that is relative to thread 16 here. And I guess that's pretty much all I had to talk about today. But we encourage you to give all these techniques a try, including DDT, and let us know if you hit problems, or let us know if it works out well. So, any questions? Anything that has anyone already run into some issues where you've used some of these techniques? Not yet. Maybe you'll hit some later today. So let us know if you have any troubles.